Hey guys, we're in the last video for chapter 3 and this topic in chapter 3 will take you straight to chapter 4. Okay, so when you're solving chapter 4, I am sure you will definitely have to go back to chapter 3. So while you're watching the video, please pause and take notes. Okay, so this video we're going to discuss about the first law of thermodynamics. So in chapter 1, we have discussed about this a little bit. The first law is related to conservation of energy. Okay, and conservation of energy means that energy cannot be created, energy cannot be destroyed, it can only change forms. So we use this example, this exact example. Okay, so where at the top of the hill, the object has high potential energy because of the height, and 0 KE, zero kinetic energy because it's not moving. As it falls, its potential energy will drop because there's reduced height, and the kinetic energy will increase because of the increase in velocity. So in both cases, the total energy is still the same value because of the first law. Okay, because energy is conserved, that's why the total energy is the same. Here also is another example. If you're cooking a potato, for example, in an oven, how much energy increase in the potato will be exactly the same as how much energy or how much heat you've learned about this. Q in is heat in. How much heat do you put into the potato? That will be the increase, delta E in the potato, because the energy is not gone anywhere else. It cannot disappear magically. Okay, there are some other examples here for you to understand. You're cooking, I don't know, maybe rice or Maggi. You put in heat 15 kilojoules, but the delta E inside the pot is just 12 kilojoules. That means you have 3 kilojoules missing. That is not magic. Okay, the 3 kilojoules of heat that is missing is simply heat lost to the surrounding. Of course, when you cook, you feel hot because you're standing next to the pot. That means it's already inefficient. The heat is lost to the surrounding. Okay, but of course, in certain processes, it's difficult to control that. You need to have, what's the word? You need to have insulation if you want a completely efficient process. But let's talk about that later. Okay, here we have a system. We have a battery. This is supplying electrical work in the quantity of 5 kilojoule. Okay, it's supplying electrical work. So notice this word adiabatic. Adiabatic here means no heat transfer. So what's the meaning of no heat transfer here? What? Okay, no heat transfer means that there's no heat loss because you are putting in so much electrical work inside the system. There will be a heat loss to the surrounding. But because of the system being adiabatic, that means it's insulated, you will not have any heat loss. So the delta E inside the system will be 5 kilojoules. Unlike this one has no insulation, so the heat is lost. Okay, another one, we have shaft work in because the shaft is rotating from outside and it's rotating the content inside here. It's being powered by something else outside. So that shaft work in is 8 kilojoules. Again, the system is adiabatic, so the change in energy inside will be 8 kilojoules. No losses to the surroundings. All right. Now let's look at the energy balance equation. Energy balance is simply the change, blah, 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 blah. It's a very long definition. So let's look at the simple one. Energy balance simply means the total energy entering the system minus the total energy leaving the system equal to the change of energy inside the system. This makes sense. You eat, that is energy entering the system. You do exercise, that's energy leaving the system. What's left is the net change. Okay, straightforward. Oh, you can read this, of course, if you want. You can pause and read it. So in equation form, there's E in for energy entering minus E out for energy leaving. Why negative? Because it's leaving. So minus it equals to change. Okay, so here we have a piston, and this B here is boundary work. You don't know it yet. We'll see it more in chapter 4. Okay, but enough to know that this is a type of work that is moving the piston. So that work is 10 kilojoules. The system is adiabatic. Remember, no heat transfer. So the delta E is 10 kilojoules. Okay, I think we have one more. Okay, here we have shaft work in 6 kilojoules, but there's no insulation, meaning that it's not adiabatic. At the same time, you also have heat in. Maybe you are uh, applying some source of heat to the system. So there's Q in going in. So in total, we have shaft work in and we have Q in, but we have Q out because of heat loss to the surrounding. So in total, we have 18. Okay, 15 minus 3 for the heat plus the 6 for the work equals to 18. That's how we use this equation. Very, very simple. At this point, if you are not clear, you can rewind. Okay, I'm going to proceed. Okay, now let's talk about the delta E part in the equation. So we had this equation from the previous slide, remember? So let's talk about this delta E. Delta E or delta anything is simply the change, final minus initial. So it's the same for delta E. It's the energy in the final state minus the energy at the initial state. 2 minus 1. Alright, so I hope you remember this equation. Total energy E, okay, or basically just energy of a system is the KE, the PE, and all the internal energy. This is total energy of a system. So if you want to look for the change in energy or the delta E, you have to look for the change for each of this component. What's the change in KE? What's the change in PE? What's the change in internal energy? So we have this equation. Okay. Now, delta U can be calculated using properties from the uh, property table. So you know that capital U is mass times small u, right? Now, since we want change, so it has to be U2 minus U1. Y times M, because this is per unit mass. This is from property table. Mass is the mass, multiply with mass, you get total internal energy. KE is the same thing, half mv squared, just like in the question that you saw, I think in the previous video. PE is also similar. Okay, and please be mindful that these two, KE and PE, will give you the answer in joules only. So you need to still divide by 1000 to get it in kilojoules. Okay, a special case. If you have a stationary system, that means there's no elevation at all. So no PE or no change in PE. Z2 and Z1 are the same. Therefore, this will be 0. The change in PE equals 0. Same thing with velocity. If the system is the same, has the same velocity, maybe 0 for both cases. So the change in KE will be 0. So in a typical system where the entire system is not moving, it's not changing the levels, that means it's not moving at all. So you only have the change in total energy as a change in internal energy. So this is often the case. All right. So you've seen all this, right? Work and E and delta E and KE and all this. So what do you do with all this information? Okay, so don't worry, this slide will explain. So what you'll do with all that information is we will put them into this energy balance equation. So this is called energy balance equation, the name of the topic or of the video. E in minus E out equals delta E. Energy in minus energy out equals to change in energy. So E in and E out, there are only two types of energy transfer, right? If you remember, there's heat and there's work. So we can write the work portion first, and then we also have the heat portion. So the work, of course, can be shaft work, electrical work, spring work, and all that. Let's just call it work for now. And we have the heat in minus heat out. And on the right side, we have delta U, delta KE, and delta PE. This is a full equation. This is the energy balance equation. This is the expanded energy balance equation. This will follow you until chapter 7. So write it down and remember it. Okay, and most importantly, know what it means. You should be able to explain what this equation means. So this equation applies to all closed systems. Why closed systems? Because open system is another story. That's chapter 5. All right, so closed systems means fixed mass, not fixed volume, because volume can still change, but fixed mass, and that is closed systems. Okay, so we have this equation, capital E, unit is kilojoule. What if you don't know the total E in and E out and all that? What if instead you have the rate of energy transfer, which is in kilowatts? Okay, maybe you have the total time. What is the change over time? What is the rate of energy going in? What is the rate of energy going out? So it's the same thing. It's the same equation except that it's divided by time. So all the terms, you just put the dot there. Doesn't mean you can simply put that and just use the same values. This means that the values have to be per unit time. All right, we'll use it and then you'll understand it better. So the unit, of course, is kilojoules per second or kilowatts. So we use this when energy transfer rate is known instead of total amounts. The easiest indication to tell you whether to use this equation or the previous one is when the question itself gives you values in rate. Gives you the heat transfer is 10 kilowatt, for example. So that watt tells you that this is a rate of heat transfer. It's not the total heat transfer. Okay, and whenever you have time given in the question, the process happens for 10 seconds. So that indicates that it has something to do with the rate of energy transfer. All right. So I'm going to end this video here because it's getting long. We will discuss examples when we meet, or maybe I'll create a video for you. Okay, but for now, this is all the topics. So we have 3.1, 3.2, and 3.3. And depending on when you watch this video, at the time that I'm recording this, you will have your test on the coming Wednesday. Okay, so make sure you really understand these three topics in chapter 3. Okay, I'll see you again.